So yeah, doing webinar number 7. Um, yeah, you notice I'm going to try to keep volume down here so that WCC and not disturb our students, I guess. All right, so yeah, this is just continuation of NN and CNN. Um, yeah, so this is an example of how to calculate the number of parameters for linear model here. This is image to 28 by 28 in classes. You get well, uh, yeah, so 7,850. It's because you have the weights for each one of these pixels here, and do that 10 times, and you also do the bias here 10 times. You put it in here. And yeah, it's just equation summarizing what was example 4. Um, so there's some things about nice properties about linear models. They are limited representation by easier to um, compute, and very good for because like we can send small change in the input will result in a small change in output, which works. You don't want your output to suddenly jump by like 10,000 or something, and then suddenly your model is out of whack, right? The virtual linear equation is constant, very stable. For that, it's back to a markup. And so there's some drawbacks here. This one is one of the drawbacks. I had hard time representing anything that's nonlinear. Multiplication, for example, if your variables have a quadratic relationship, don't do that. So in other words, you have to introduce nonlinear somewhere. So Relu is a linear function that's pretty utilized for deep neural nets. Um, neural nets in general, you can use you don't have to use Relu. You can use sigmoid or 10 other nonlinear functions, but there is a let's say vanishing gradient issue, which is causing it essentially your gradient doesn't propagate all the way back up to your deep layers. Right? This is property of Rebel essentially. When x is positive, y equals x, otherwise y is 0. So the derivative is like that. Right? Constant over here, 0 here. And it's a example of Rebel activation from capacity. So you have instead of just doing by one linear unit, you have a linear unit connect to Rebel, connect to another linear unit. Then you have your softmax here. You get the one hot encoding. Back to the right. Let's go through an example. This is an example. This is the type 2 example for showing what ReLU is doing. So let's see. Let's run it through and see what happens. You see that this is there's two positive numbers here. There's 0 and there's two positive here. Okay. And let's see what actually happened here. This is the first. This is going from the first input layer to the hidden layer, and you can see that these are numbers. There's a remultiplication here, and these are negative, and then you multiply them again by the weights of the output layer, and it's like this. And our value will change these to 0. And see that's what I did here. And there's a picture of for run back application. So like we already seen it in code before, but something to note is that it takes full time memory for the block prop to happen. With this, you can somewhat estimate the memory requirements of your network. I left this here because this mainstream multiplication is kind of hard. Yeah, I should print shape of A. A is 3 by 3. B is 3 by 1. You can see this is actually yeah, that is 3 by 1. So yeah, so the dimension on the second over here we will yeah, try like that, which makes sense, but it's really just really hard to remember. That's why going to this example, sometimes you can always do this. Remind yourself. Okay, so this is in this example. These are handwritten digits coming from in this data set. This is a favorite, one of my favorite test examples for a lot of researchers, etc. Batch size 128 decreases if you have 100 memory. A small your computer have like really small memory allotments, you can decrease the batch size. Okay, so that's number of inputs. And this kind of show it's shown by example here. When on the intro video there. And we make 28 by 10. But no, this actually this has this has a hidden layer down here. And the hidden layer is 256. You can see that the weights are these are just randomly normal generated weights. These are random values for TensorFlow. This is dictionary. This is hidden. This is out. This is hidden there. This is out. This will be used down here. Mark input. Okay. Okay, so okay, that's just I just mentioned that this works fine for the in this example because there's only 274 no 784 pixels for anything larger, probably using something else. It's also only black and white, so there's not much information to do. Okay, so this is just um, one of the I think that's wrong, but essentially it's a linear equation of a flattened x times your hidden layer weights, and then adding the hidden layer bias, and then here you have the activation and output layer is bias. Output. Here define loss and optimization here for this plus is usually less than 50. The learning algorithm is the stochastic we can send loss. And cost is yeah, the cost is it's calculated by reducing the main of it's really it's the way it's named kind of weird for minimizing cost. So yeah, let's just down here let's initialize function for target session. It doesn't really like show how accurate it is or anything. Let's run for now. Well, that is saying going well. Why deeper is better than wider neural networks. So there's a few reasons: parameter efficiency, implementation. So using previously where there was the perceptron example where you stack two linear functions, it will approximate by a classification that is approximated by a nonlinear function. And it's easier to decompose the concepts from here, from lines to shapes to objects. So this is just example saving TF model. TF model kind of a pain to restore. You have to actually restore the variables themselves, which is not my favorite. And this is an example of this saving and restoration of the model. It's relatively slow. Okay, not waiting for it anymore. All right, going to the also regularization. So essentially, you can see the regularization equations here. This essentially adds to your loss this b term 1/2 of the absolute weight square. And essentially that just this becomes very large as your weight becomes large, negatively or positive. And this essentially is there to punish large weights. So it's in a sense restricting what you can do with the weights. If you want to have actually a regularized a model that's flexible enough, you can have weights that are very large and just fits your training data using it that way. And that's down here's a concept on dropout. Right? So it's all the same input, different type of representation because there are these outputs being dropped can't depend on these. It has to run them redundantly and think about in greater intuitions, just saying like it's a cat, it's not a dog, and things like that. Um, this is in the example it says is shown the ones that weren't dropped out to be times by 2. They took the average of those, but this is times 2 because it's 50%. If you have 4, or say if you have 60%, it's not going to be 2. It's going to be 1 over 60%.